morning. Good morning. Guys, I need a lot more light. Otherwise, I suggest you all stand up. You all stand up for a minute, please. All stand. 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 Yeah. Stretch yourself nicely. Okay. Because after playing some of the video games, like Ludo, I don't know what else, it takes a little effort to focus. When you feel you are fresh enough, you can sit down without talking to your neighbor, please. Thank you. So, very quickly, we are looking at prevention or mitigation. That's the first thing. Next step, we'll go for preparedness. Third, we'll go probably to response. First two is before the disaster strikes. The last is after the disaster strikes. Okay, so there's a balance between what we are doing. We saw some basic things of physics. Now, suppose you see the trace of this plot is moving up and down. It's moving up and down, and this is again probably some of the concepts of simple harmonic motion which you already would have studied. I showed in the previous class a structure which was responding to a sine wave. Okay, so we are just moving at a sine wave as nothing but a simple harmonic motion. So when I displace more, the acceleration is proportionally. When it's going to be the opposite direction, and anyway, I'm not going to go too much into that. Acceleration and displacement are proportional. Basically, that's the fundamental thing which I want you to understand. Okay? So in our case, displacement is at the bottom. Okay, example we gave, I'm standing on the table and one of you shakes it. Yesterday I was traveling by train. You would have noticed this. When the train is riding rough, you tend to lose balance. And this is exactly what happens even in your structures, which are subject to earthquake. Of course, we saw some geological aspects of earthquake also. We see that there are three parameters: amplitude, frequency, and of course there is an input function. In our case, input function could be the sine wave. When we are studying earthquakes, we typically take a collection of plots and then try to reduce it to a very simple form. But that again is too much of math. That's the math which we do. We will not bother you with those things. But what I want you to understand, there are three things which are very important: amplitude, frequency, and input function. This tank, water tank which we are showing, is what I call as a single degree of freedom system. The entire mass is concentrated on the top of the water tank, right? The water column on which it stands, the vertical structure, essentially is like a foot ruler, what we were talking in the previous class, except that it's placed what I call as vertically, and the mass is kept on top. So that accounts for the stiffness of the system. The material which makes up the water tank contributes to damping. Okay. So this is a very simple example. Now watch this video. This is a very nice and this is a video which I feel is very interesting, which will help you understand this. I'll have to open this in. I don't know whether this is downloaded fully. Let me open this one, which is actually downloaded properly. VLC player. This couldn't be put in the presentation because it come forward. Now watch this. Three parts, three systems are there. Different stiffness. The moment you look at it, you can say different stiffness. They are all going to be vibrated on a shake table. What you see is a shake table. You can shake with fixed frequencies. So they are slowly increasing the frequency. We are talking about response. Response means how much it's going to react to an input function. Okay, in this case, our input function is simple harmonic motion as good as a sine wave. Okay. So, you see, they are slowly increasing the frequency. For various frequency, just observe what happens. I'll leave you to be the judge. First bench. Sit in the first bench here. Don't run. what did we observe? See, at different frequencies, different systems got excited, right? Different, what I call as the stiffnesses. Stiffness was the only parameter which we changed. You will also, I have another video which is a little more explicit and which should probably reinforce these concepts to you a little better. Okay, a little more. Now, you see that when the height is less, certain things happen. When the height was more, certain things happen. Now, I'm going to again go back to this, what I call as the response which I showed you here. Now, look at this. This is the first mode of vibration. I don't know whether the video is playing. Yeah. This is the first mode of vibration which we have. Just hold on. Okay, actually it's quite interesting to watch as a video. Now, for some reason I'm not able to get it to play. Okay, no problem. You will see that the first mode was a translation mode where it was only shaking the x direction, and in the other modes we saw that it was moving more in the y direction and so on and so forth. Third mode was a twisting mode. And yeah, the ones beyond that were not. I mean, they are also having certain masses which were excited mode. Okay. Now have a look at this one. I hope this works. Okay, again, this video is not playing for some reason. This video, I think I can show it to you again on. This one on the, yeah, I can show this video right here. I'll open it with
when we see this kind of picture, it's Mexico earthquake. See that small buildings collapse and not hard buildings. So it's a real problem. And what kind of problem is? It's a problem of resonance. So buildings resonance. So to understand this phenomenon, we can make this experiment with the same screwdriver, automatic electric screwdriver, with an eccentric here. And this system we can switch on, off, and also increase the speed. We have different building, different parts, and I'm going to make the system working to show to understand what is the resonance phenomenon. So with this system, I can increase the speed and nothing appears because the eccentric is not far from the axis. So now I'm putting this far, and now I see the beginning of the working, this system working. So now I'm going to study resonance. We can see that the big buildings resonance. I'm increasing the speed. And now we have a big building, and now the intermediate building resonates. And I increase again, and I see the small building resonating too much and no foundation, so small buildings collapse. Maybe exactly like that, but it's not a problem of foundation. Here it's a problem of size. So to change the resonance frequency, it's possible to prevent resonance. So put a big mass on the building like that. And so the building does not resonate anymore. And I can solve the new resonance because the building is going to resonate, but in a low frequency. Like that. So the new frequency of resonance is this one. The prevent resonance. It's also possible to put a big mass, and the building resonates at low frequency. As you can see, the big mass is fixed, and the building has a big resonance. So now we are going to make the mass free, removing the scratch here. When the mass is free, the system is an amortissement, and as you can see, the mass moves, but not the building. So if the system which is used in Taperi power and the computer are pushing or the big mass to prevent the resonance of this building.
Right. So basically, what did we see here? We see that we are able to change the resonance of the structure very suitably. I'm not going to go again. I'm sorry, this every time there's a change in the video, the whole thing, there's some problem with the detecting of the signal. Right. So we had a video earlier where we showed the soft story collapse in Mexico. So now basically I don't want to go into all the horror part of an earthquake. Okay, what I really want you to think is that earthquake is also one of those things which we can have under our control. Okay, we will see some of the things that make a structure behave better in an earthquake. Okay. First and foremost, we found that timber structures typically behave well in an earthquake. Okay. Then steel structures behave very well. Suppose they are detailed properly. That means the connections, what we do as civil engineers, it should be proper, where it can take the loads which are coming on it. Okay. And we have what are known as well detailed concrete buildings. In other words, if the steel reinforcement which is there is placed properly, okay, and detailed properly in the sense, we found that most of the times the beams links, the main rods are there are some things which tie the reinforcement, they open out. So suppose you are preventing it from opening out, that means it's a well detailed structure. Then of course we have masonry reinforcement. If they are confined or we don't let the masonry elements split out during an earthquake, then it is safe. Masonry units are, for example, the brick walls, maybe the blocks, the other stuff, whatever you see in the walls, if it is standing on its own and then supporting the roof. Typically you see it in the much older constructions. So masonry structures can behave well provided the units are confined. And again, if you look at it, even the concrete structures are told to be well detailed provided they have proper confinement. So the word I want you to remember is confinement of structures. The other thing which really protects us in the event of an earthquake is when there are multiple load paths. Okay. So there is a lateral load. Is there more than one way this lateral load can be transmitted safely to the foundation? This is the second thing which we typically try to see in ensuring that a structure behaves satisfactorily in the event of an earthquake. So if you see, this is a frame where we got some cross ties which are used for transmitting the lateral loads. And then of course the last one is the moment resisting frame, which essentially is detailed so that any turning of the beam column or the beam and column which occurs is effectively taken care of. All of these are ways by which a push on the system is resisted. Okay. Please see it in light of all those videos which we showed, especially the previous one where we saw that there is a frame and if suppose you see there is a lateral load or this is what we call as the longitudinal load along the direction of gravity. Away from gravity there is a load and these loads are what we are very much bothered to take down safely. So if you are able to notice that there is more than one load path for a structure to transmit its lateral loads, then you can say that the structure is safe. Okay, so if you want to know whether the building you are living in, maybe a hostel block, is going to be safe in the event of an earthquake, first thing which you probably will go and see is whether because you cannot see what is inside, how the reinforcement has been done, nobody can know, even we don't know, unless we are going to use some of very, what you call as, good scanning tools, and nobody does it. But what you can do, you can at least see whether the structure is having multiple load paths. The other very important thing probably is where we look for what I call as soft stories. In one of the previous videos, I showed a structure just collapsed down. But because the bottom was having car parks, there was no infill walls. So there was a change in stiffness between the lowest floor and the floor above. This change in stiffness typically concentrates most of the forces. Okay. So the other thing is, so if you are having, these are some of the concepts which we have for providing a load path. So this is a typical frame which we have. This is what we call as a structure with shear walls, and here we are having some bracing system. So you can have a bracing system. You can have any of these things which will help you create alternate load paths. Basically. So you see that the shear walls, there are multiple shear walls. Any one of this, even if it fails, you will find that there is still some other system which can take the load downwards. Back to the foundation. When I say downwards, to the foundation. Again, we have some of the very fancy shapes in many of the sorry, I don't know what is wrong here. Yeah. So we like to, there are many fancy shapes like C, T, L, H, which are in earthquake engineering poor practices. So typically we try to separate the structures. You can see this in, if you go to GDN, you see very nicely the expansion joints. Even in this building, you can see expansion joints. There will be two columns close to each other. There will be some rubber or neoprene or some other material which is put in the gap to prevent water from flowing. Now what has happened is, this building, what is the shape of this building? It's a hexagon. It's not a regular shape. But what have we done? We have made the irregular shape into more regular parts, thereby improving the seismic performance of the building at large. So you can actually see expansion joints in this building. I even suggest you go and try to take the expansion pictures of the expansion joints in and around our own campus. Okay. Now I'll also put one more thing. If you go to this one, Silver Jubilee Tower, okay. SJT, is it a regular structure or a irregular structure? Sorry? Regular? Okay. Now, does SJT have expansion joints? Yes? Where? All of you, most of you are from SJT, right? Okay, TT, okay. Where is your class? Where are your classes? SMB, okay, great. I have already given you this as an example. So I just want you to walk around the place, look for what I call as the way by which they have made the structure improve the performance of the building. Okay, anybody in Q block? Nobody in Q block was in Q block, right? Yeah, so you can see shear walls in Q block near the lifts and other things. This always will be there in all the high-rise structures. Okay, go and see the load paths which they have given for the structure. Using this as a reference, whenever you are suspicious about the seismic performance of a building where you are living in, or an office building, you can always go and take a call. See, this is why, like I told in an earlier class, when the earthquake struck when I was working in L&T, I was very sure this is a very nice design. Nothing is going to happen to the building. If this building is going to get destroyed, earthquake is going to be of such a magnitude that even if I go out, I am going to die. Okay. So this kind of confidence can your buildings give? Probably that's the question I leave you. The other very important thing is vertical irregularities is bad. Vertical irregularities is band. Okay. Now you look at SMB. Is SMB having vertical irregularity? That means along the height of the building, there is a irregularity in the loading, or there is irregularity in the stiffness. Okay. See, soft story, the wall below doesn't have, the floor below didn't have walls. So when the earthquake struck, there was no way by which the force could be taken in a diagonal. There was no diagonal strut. In the previous thing I showed you that there was some kind of bracings done. The walls can behave like that bracing. So what has happened? The floor above had the bracing pattern, but the floor below did not have the bracing pattern, so they collapsed. See, the thing is, all the earthquake videos live now, everybody is having mobile, everybody is shooting, and all of them are very heartbreaking. In the sense that I wanted to show you the class some of the more gory videos. I was reviewing a lot of videos. I thought, okay, guys who want to look at it or more having the heart for it, they can do it by themselves. I don't want you to bring the gore part. But look at, you go home and watch some videos, see the way the buildings collapse. Try to understand why they collapse. You find that one of these things, plan irregularity or elevation, irregularity in elevation is there. It can be an irregularity of mass, it can be an irregularity of stiffness. Damping typically will not contribute too much. Typically the whole building is made of the same material, so the damping is a constant factor. Okay? So this is what happens when the L-shaped building is there. Each part tries to move differently and more. So this is going to cause what I call as excessive forces to be set up in the system. Okay, you can design to resist the forces, but there is a fine line between being economical and being super conservative. So always economy wins. In other words, if I can build a house in 10 lakhs, I will not want to spend 12 lakhs easily unless it really warrants it. So yeah, with this I'll close what I wanted to show for today. Basically, we have seen how real structures behave in the event of an earthquake. In the previous class, we had a session where we tried to observe how the earthquake is going to, we did some mathematical calculations and then worked out the deformed shape. The software is essentially doing that work only. It is doing a lot of calculation. Essentially, it is solving a lot of matrices, and then it gives me what are called as the eigenvalues and eigenvectors. Okay, you would have done this eigenvalue problem in your branch for some other work. Okay, mechanical engineers, I have no doubt your vehicle dynamics has eigenvalues and eigenvectors. Computer science students, you might have done it in your math without knowing where it is being applied probably. Okay, so this is the place where we apply eigenvalues, and this is one of the places. Where we apply eigenvalues and eigenvectors. Okay, so on and so forth. We saw how real buildings get affected by earthquake. Previously, we saw how excitation takes place. Excitation takes place because of a release of energy under the earth. This passes through various medium, gets reflected, refracted, and then it comes to the surface. And there it causes a ground motion. This ground motion is what causes the vibration in the buildings. Most of them have a simple harmonic motion. Just the way we talked about standing waves, where we have a bed sheet, I shake the bed sheet, the wave is getting transmitted, right? Or it's going to throw it up and down. One of these things are going to happen. Or there is the love waves. This is a combination of whatever I'm talking about. And we saw some of the safer ways to configure a building. Don't think of being very fancy, having a tower in one side like one of the old time castles. Try to keep your masses as far as possible to the center of the building. Try to ensure that the mass and stiffness are uniformly distributed along the plan and elevation of the structure. With this concept, I feel that you have enough knowledge of building to go and talk to the civil engineer. This mass doesn't look good. Half of the people do not understand what you are saying. but then they get very careful. Oh, I should do something about this. He's talking about mass, he's talking about stiffness. So they either come to you with a whole bunch of calculation to prove that what you've done is safe, or they are going to go back to the drawing board. Okay. Any questions till now? Any questions? Okay. So you just remember, different heights means different stiffness. Different frequencies means different responses. Okay. So tomorrow's quiz is between 10 p.m. and 10:50 p.m. Okay. So I will probably be focusing more on the ways by which you can make a building safe against earthquakes. Okay. I'm primarily looking at how I can make the buildings safe against earthquakes. One of you can take a picture, share it on the WhatsApp group. Please do it right now. You can take a picture of this. Are you on the group? No, nobody's in the group. Are you in the group? WhatsApp group of a class? Okay, are you in the WhatsApp group? Yeah, just come, please take a picture, put it on the group right now. I intend to put this slideshow online, but God forbid if I get delayed or something, I don't want you guys to suffer because of that. Yeah. Now, those of you who have not got yourself on the WhatsApp group, this is the link to the WhatsApp group, and these are some of the resources which I used in developing the content for you. Okay, and especially this iris.edu. Okay, I discovered it this morning. It has all the what I call as the reflection, refraction, and other things which I talked about, right? And also the analogy of the sun which I gave is explained differently here. I have not gone through the materials they have done, but I know for a fact that it should be good because it was exactly what I was trying to explain to you guys in the class. These are the videos I used. The last one, preventionweb.net, is the place from where I took all my photographs. I mean that what I call it, the images to show how how the structure should be done. Guys, if you want to know much beyond on how to make your structure really safe on earthquakes, you need to just understand how to detail the reinforcements. Okay, how the reinforcement has to be arranged, how you have to tie it. Okay, I can, if you're interested, we will have a separate session on that. It will be informal, that doesn't have anything to do with your exams. It's more like on your demand, we will have it done. Okay, any questions from today's class or tomorrow's quiz? Anything? Okay, thank you, great. See you then on Monday.